In this screencast, we'll talk about the idea of solubility, which is the maximum amount of a substance that can be dissolved into a specified amount of liquid at equilibrium. Let's say we have a block of potassium nitrate salt, and we drop that block of salt into a beaker of water, and the salt will fully dissolve until it reaches a point where no more salt will dissolve. So this is what describes a saturated solution. A saturated solution is a solution which contains as much of a dissolved species as it can at equilibrium. If the solution were not saturated, we could keep adding more salt until eventually no more would dissolve, and at that point it would be saturated. So now what happens if we reach saturation but then decrease the temperature? Generally, when we decrease temperature, solubility will decrease. Let's look at the solubility of potassium nitrate. So say we cool the solution quickly, we'll be coming down from some saturation point on this line, and as we decrease temperature, the solubility of KNO3 will decrease. If we started with a solution that was saturated at 80 degrees C, and we decrease the temperature to 40 degrees C, the amount of KNO3 in solution will be greater than the solubility at 40 degrees C, and this constitutes a supersaturated system. A supersaturated solution is when more solute is dissolved than the solution can hold. Generally, this is done as described here, where we dissolve to the saturation point and then decrease the temperature. A common example is if you were to dissolve sugar in water and then heat that water such that you could dissolve a large amount of sugar. Then later, we can cool that water with some form of substrate in the mixture, and in this case form rock candy, as the sugar will come out of solution slowly from its supersaturated state. So what's important about this system is that we were able to reach a saturated solution quickly by heating the water and adding sugar. But when we cool the liquid, the solution stays supersaturated. The solubility of the solution does not tell us how long it takes for the system to reach equilibrium. So slowly over time the rock candy will form, but it won't happen immediately. Typically, as engineers, we will use systems where the liquid is saturated with a solute but not supersaturated. So if our system is saturated, we can use our solubility chart to determine solubility based on temperature. So going back to our KNO3 example, we might say we have saturated water at 50 degrees, and we can use that temperature to look on our chart at the KNO3 salt and see that at 50 degrees we have a solubility of around 85 grams of KNO3 per 100 grams of H2O. And it's important to remember when using these charts that this is a ratio of how much salt is dissolved in the liquid, not a mass percent. So there's not 85% KNO3. So to figure out what the mass percent of KNO3 is in the liquid, we would need to use another equation and say that X KNO3 equals 85 grams divided by 85 grams of KNO3 plus 100 grams of water. And this is going to give us a mass fraction for KNO3 of 0.46. So this gives us the mass fraction of KNO3 once saturation is reached, but it tells us nothing about how much time it takes to reach that equilibrium. So in dealing with any of these solubility systems, remember that our charts tell us what the system will look like at equilibrium, but says nothing about how long it will take to get there.